Okay, in this problem, we are looking at acid catalyzed reaction of an aldehyde with water to form, hydrate. Since we are doing this reaction in acidic medium, first thing that is going to happen is the oxygen is going to grab this proton from the acid and it's going to get protonated. Then when it gets protonated, this is one resonance structure, and here is another resonance structure. So when you look at this two resonance structure in this one, there is a positive charge on carbon. Therefore, this carbon is electrophilic. Now this carbon is susceptible for an attack by water. Then water will make the attack, and when the attack is made, then we get water with two hydrogens and a positive charge on it. Then we need to remove one hydrogen from this oxygen so we can neutralize that charge. So water will act like a base and remove a hydrogen, and then we get the hydrate from an aldehyde, which is colorol. In this example, we are looking at the hydration of a ketone, which is acetone, in basic medium. So since this is done in basic medium and hydroxide ion is such a strong nucleophilic species, it's going to do a direct attack on the carbon. And when the direct attack is done, then one of these pair is going to shift on oxygen. Then we get this intermediate. Then when this intermediate is formed, the oxygen is a basic oxygen. Then it will grab a proton from the water, and it will change to a hydrate. In problem 1815b, we are looking at formation of cyanohydrin from a ketone. And in order to form a cyanohydrin, the first part of the reaction is the reaction of cyanide ion, which is used, as a sodium cyanide or potassium cyanide, paired up with the hydrocyanic acid. Then cyanide ion will attack the carbon, and when the attack is made, one of these pair between the carbon and oxygen is going to shift, and it's going to give us this intermediate in here. When the intermediate is formed, then the oxygen uses one of these pair to grab a hydrogen from hydrocyanic acid. Then the cyanohydrin is made. In problem 1816a, we are just looking at what happens when you treat an aldehyde or ketone with sodium cyanide, potassium cyanide in presence of hydrocyanic acid, and then all you know you're going to get the cyanohydrin. Here is another example of a reaction of an aldehyde with the cyanide ion in presence of HCN, and further solution being acidified. And like in this problem, the first step in here, we get hydroxydrin. But when hydroxydrin is hydrolyzed with the acetic acid, with any acids, then what we get is carboxylic acid. So this is something that we need to learn and know about it in the chapter that is covered carboxylic acid, when we are looking at the synthesis of carboxylic acid. Here are some examples of reactions of aldehydes and ketones with nitrogen containing compounds. And the nitrogen containing compounds could be many different types of compounds. As I said in other videos, your nitrogen should contain at least 2 hydrogen atoms for the reaction to happen. So when the reaction happens, we get what is known as imine or shift bases. And these type of reactions, as I explained in a video for the lecture, these are condensation reactions. You get a water molecule, but water molecule here is not shown. So these are the examples of the reactions of amine or amine derivatives with aldehydes and ketones. And your amine could be aromatic or non-aromatic. Here are some more examples of the reactions of aldehydes and ketones with different type of compounds that has nitrogen with two hydrogens, and like in here in this compound we have two nitrogens, and on each we have two hydrogens. Regardless of what kind of compounds are used, if you have at least one nitrogen with two hydrogens, then you get that double bond being formed between the carbon and nitrogen, and then you lose two nitrogen from you lose two hydrogen from this nitrogen and oxygen from your aldehyde or ketone, and the other product that is not shown for any of them is water. So these are different examples of reactions of aldehydes and ketones with nitrogen containing compounds. And remember, these are pH sensitive, and you need to be sure that the pH is around 4.5. Here are more examples of the reactions that we have covered in the previous slides. You could look at these reactions from this side too, like you could be given a question like this one, and the question would be which carbonyl and amines were used to make these. So all we need to do is separate where the double bond is between the carbon and nitrogen, and to the carbon we add an oxygen, and to the nitrogen we add two hydrogens, like it is shown in here. Like in here, you would break up the double bonds in here. To this nitrogen you add two hydrogens, and on that carbon you add an oxygen. Same thing in here, you break up the bond there, you add two hydrogens on the nitrogen, and you add the oxygen on that carbon. In these two problems, you could be learning how to make acetol by treating aldehydes and ketones with 2 moles of alcohols, because if you just use 1 mole, you get the hemiacetol. But if you are using 2 moles of the alcohol, you get the acetol. And again, remember, these type of reactions are done in acidic medium. The acid is not shown, but this type of reactions happen in acidic medium. So to make acetol, you need to pick the ketones or aldehydes that are needed and the alcohol that are needed for the synthesis of the acetol. So if you look at it this way, you are making acetol. You could look at the problem this way, like the question like this could be given to us, and they would ask what alcohols and what aldehydes or ketones are used to make the acetol. These groups in here, they come from your alcohols. So it means your alcohols, they lost protons. That's why you have the alkoxy groups in here. Your ketone or aldehyde lose oxygen. So in order to separate these, you separate these two groups, and you add hydrogen to each alcohol. Then to your aldehyde or ketone, you add an oxygen. You would do the same in here. In problem A, we are learning how to reduce aldehyde but not ketone. Because if we add NaBH4, NaBH4 is going to reduce both aldehyde and ketones to alcohols. But if you are just planning to reduce aldehyde, then you need to modify NaBH4. And in this case, see, NaBH4 is changed to NaBH-OAC3. So that's the acetate form of NaBH4. So you're making NaBH4 weaker reducing agent. And since aldehyde is more reactive than a keto group, then only aldehyde will be reduced. In problem B, we are learning how to protect aldehyde if we are just going to do the reaction with other, another type of functional group, like in this case, a carbonyl group that belongs to this ketone. Because if you look at the, this reaction really, if you start from here to there, you see the reaction happens on the keto group, not on the formyl group. So in order to make sure that the reaction happens here, not the on where the aldehyde is, then we are going to protect this aldehyde group first. To protect this aldehyde, we are going to use this diol. And when we use this diol in presence of acid, then we get this cyclic acetal. When the cyclic acetal is formed, then this is not aldehyde anymore, and is not very reactive toward a Grignard reagent that we add later, and Grignard reagent is going to attack the oxygen. And then when you acidify the, your Grignard the reagent after it is formed, then you're going to get the alkyl group, which is the methyl group, being added to that right there. Okay, and then in order to get your aldehyde back, since you are adding acid in here, the aldehyde, the acetal is going to change to aldehyde. In these two problems, we are learning how to make alkene from aldehyde and ketone using Withing reactions. What we are really interested in here is to see in what order we need to add these reagents that are needed in order for the reaction to happen. So the first part of the reaction is to treat your alkyl halide, and it's preferred to be primary alkyl halide, with the triphosphine phosphor, and then you add your butyl lithium. So this is the order that you add them. You get the yelid in here. We don't really have to show the formation of the yelid. Then you add your aldehyde or ketone to get the alkene. In these two examples, we are learning how to oxidize aldehyde. And if we are just going to oxidize aldehyde, we can use silver oxide, and silver oxide easily oxidizes the alcohol to carboxylic acid. And the silver precipitated out as the silver metal, and this is known as Toluene's test for aldehyde. And here, this is what happens when you treat the aldehyde with the strong oxidizing agent. You get your aldehyde oxidized, but at the same time, you get any other functional groups that you may have and be susceptible for oxidation will oxidize also. Like in here, there is a OH group, and OH group got oxidized also. But in this case, the OH group did not get oxidized. Here are some examples of deoxygenating aldehydes and ketones by different reducing agents, like we have in here Clemmensen reducing agent, the zinc, hydrochloric acid, water, but zinc is mixed with mercury. So as you can tell that the oxygen is removed, the hydrogens have replaced the oxygen. This is Wolff-Kishner reagent that does the same thing. It takes the oxygen off from there. And this is a Wolff-Kishner reagent also. And this is a Clemmensen reducing agent. But the difference between using these two, when you look at this, you will notice that this will reduce everything, but Wolff-Kishner reducing agent does not reduce your cyclic acetal.